Just one more check. Everyone can hear me okay on Zoom? Even if I'm talking like this?
Sounds good.
Oh, okay. I need to change the output, so goes to one more check on Zoom to say something.
Sounds good.
Okay, great. Thank you. All right. So let's start off with a correction for homework 3. So I think one of the problems in homework 3 was calculating these expectation values of, some initial state. I think L equals to 2, M equals to -1, right? And then for like, LZ, for example, right? Since LZ is not going to change the state because this is the eigenstate of LZ already, then you basically just get, -1, and then you have the expectation value between these two same states, right? So just write them the same, right? This will just turn into 1, and then you get -1 as the expectation value. But one of the things that some of the students noticed was that, well, if you do the same thing, for example, for the L plus operator, right? What happens is that, right? This will give you an expectation, a value out here. I'm not going to even try to calculate it. This is just an equation. But what's going to happen is that you end up with L equals to 2, M equals to -1. But then since you raise this M by 1, right, that's going to be L equals to 2, M equals to 0. And this is actually going to be 0. And anything times 0 is 0. So therefore, right, these expectation values are going to be 0. What I meant to write is actually just for you to calculate the eigenvalues of these states, okay, as opposed to finding the expectation value for L plus and L minus. But I did wanted you to calculate the expectation value for LZ and L square. But then when I squish those two problems together, I should have it differently for both of them as opposed to squishing them together like that. Okay. So so in the solution, if you put, the answer that I originally put, where the expectation value of here is like, I think it's 2 times 2 plus 1 minus -1 times, well, I'm going to write the variable version so that people know what I'm talking about, right? If you wrote down the answer to be basically L times L plus 1 minus M, so this is the plus operator, so M plus 1. So whatever this number equals to, just mark that as correct. But then if you put 0, that's also correct, okay? That was just my mistake. All right. Any questions about that? It's a correction in homework 3. Okay. I remember homework 4, I pushed it back to be due on Thursday because we're actually trying to finish up everything we need to do on homework 4 today. So I want to give you more than one day to finish the homework. And I think there was a question on the exam, right, where we're going to have 5 problems on the exam 1, right? And these are going to be about 10 minutes problems. So they're not going to be like, for example, if I go to homework or something like that, right? Well, I don't want to show the homework 4 stuff yet. So in 10 minutes, you will not be able to do number 2 on homework 3, right? Right, because I can't even put it on one screen, right? Right, so there's like 15 lines of algebra there, right? However, right, what's a good example of a 10-minute problem, right? Right, so like doing these commutation relations, right, between Lx and Ly, right? That you can do in 5 to 10 minutes, right? Okay. Another example of problems that you can do in 10 minutes is, well, these expectation value things, maybe I'll just have a revisit of that just to correct things, right? These you can do in 10 minutes, right? Okay. Like a lot of the Lorentz transform stuff, right? Some of them are pretty long. Let's see. There's one long one, there's a short one. I'll show you guys. Right. So these, four vector problems, right? You can do them. So things that are like, 5 algebra lines long, right? Those you can do in 10 minutes, right? Because it'll probably take you like, 3 or 4 minutes to figure out what to do first. and then another 5 minutes to check through all the algebra, right? And that should be the length of these problems, not, not that's not homework 4, that's the solution. Not this one where you have, what was it up here? Where we're trying to do the show that momentum in quantum mechanics is just mass times the expectation value of momentum, right? Where there's about 15 lines of algebra, right? And if you don't do each step, right, the most efficient way, it'll turn into 30 steps of algebra, right? So this is a problem that it takes like 30 minutes to an hour to do, right? That's not going to be on an exam, right? So just note that what you're studying for is not these long proofs, right? But it is important to know, how you deal with commutation. This is just a practice, right? And on the exam, you're going to be doing a short version of these things, okay? Right. Okay, any questions? So I think we're going to have our review on Friday because since we pushed the homework to be due on Thursday, right, then I can use all 4 homeworks, right, for you guys to talk about on Friday for the review. Okay, so on Wednesday, I'll start chapter 4, which is on the Klein-Gordon equation, but that's not going to be on the exam at all. Okay. Remember, exam is, what was it, March 4th? Okay. And make sure those of you taking it synchronously, make sure you have your, your camera available and then your microphone available. Okay. So I may just come in and ask you, oh, can you unmute, and just ask you questions or something like that. Okay. Just to make sure we're all taking the tests on our own. Okay. Right. And the test is open book, open internet, just not open people, I guess. So we'll see how that goes. I have the topics I want to ask each questions, but I haven't written the problem yet. So you're not going to go get the problems out of me because I don't know it either. So. Okay. With that, let's start on the control. Okay. On the last thing that we're going to cover on the exam, which is this thing called the interaction cross-section. Right. Last time we kind of already started talking about it, at least in the classical level, right? Where let's say you have 2 objects trying to run into each other, right? And basically the cross-section between them, you can think about it as kind of like twice the area. Well, the area of, let's say this is called object A and this is called object C, and you see why it's called, sorry, object B and objects. Let's do CD. Sorry, I'm keep changing the letters. Okay, right? And you can think about it as the cross-section as being just kind of like the sum of the area of these objects, right? Because the bigger they are, right, the more likely they are to run into each other. Okay, we won't rehash all the little discussion about the unit conversion and stuff like that, but just to note that in particle physics, it is generally used this weird unit of barn, which is 10 to the negative 28 square meter, right, as opposed to the natural units, which will be in inverse GV squared. So whenever you actually have to convert your calculations from this textbook, from this class, you will get your answer in inverse GV squared. You have to convert that to meters inverse, right? And then you have to convert this to barn. Okay, it's just like a 2-step process. Okay. All right, that's just a unfortunate historical thing, and I think I talked about why 10 to the minus 28 is an interesting number back in 1945. Okay. Okay. However, in Thomson, he derives the he's going to relate how the cross section is related to the thing we've been calculating, which is this transition rate, right? So all this whole chapter was all about this transition rate from some initial state to some final state, right? This thing called the Fermi golden rule. Okay, so what he wants you to do is kind of picture like a tube filled with particle B. So these black ones are particle B's. Okay, and you're shooting some particle A's through this tube, okay, which is this hollow circle. Okay. And what we want to try to figure out is how much they will hit each other, right? what is the cross section that will allow you to how much these little spheres will hit each other. Okay. Okay. So the rate of interaction, so the rate that particle A will hit particle B, we're just going to call that R. Okay, just remember it's not radius. Okay. It's going to be equal to something that we're just going to make up called cross section, sigma. Okay. Times the number of particles, the flux of particle A. Okay, so here we have, I think I wrote all the definitions down here. So this is just kind of a definition, okay, in this case, okay. And then phi A is the flux of particle A. And then of course, RB is going to be the interaction rate, okay, right? So to figure out what flux of A is, right, if you look at the picture up here, okay, okay. So this is the number of particles traveling at some speed VA along the horizontal, right? And in general, particle B could be moving to the left in the opposite direction with some speed VB, okay? So the relative speed with each other is actually VA plus VB, right? Right. Two trains crossing each other at night thing, okay? So let's keep an eye on that. Okay. Next thing we need to know is well, for the flux, right? What does the flux actually mean? Okay. If you think about flux, you just think about for some amount of time, just going to call this lowercase delta, right? Crossing, some amount of particles, delta n, okay? Okay. These are all particle B's. Okay. We can write this ratio of delta n over delta t, right, per area. I'm going to divide out that area. I know the book didn't, as basically the particle density of B, how many B particles are there, right, per volume, okay, right, times the speed V that we just derived, right, which is the sum of the two particles speed going opposite each other, right? Okay. So the flux B, right, is going to be whatever NB times V is, okay? So going back up to this equation up here, right, if we change the B's to A's and A's to B's, right, the rate of interaction with A is going to be whatever this cross section is, right, times the flux of whatever particle we were talking about, in this case, the flux of B. So just to note that, Thomson did a switcheroo on this, okay? They would place A and B in the first equation, and then in the second equation, you use B as A, okay? Okay. So this rate, right, so this is the rate of interaction if you have one A particle coming in at a time, okay? But usually you don't just shoot one particle into a beam, you will shoot a bunch of them, okay? This is known as a beam of particles, okay? So the density, so the number of particles of A is going to be the density of that flow of that beam times whatever volume we're trying to calculate this at, okay? Okay. We're just counting how many particles are flowing into your little pipe, okay? So the rate of interaction, okay, which is going to be, turns out to be our gamma Fi that we've been playing with, okay? It's going to be whatever RA is times, right, this number of particles. In this case, it's going to be lowercase n, which is the density. So this is the density instead of A per volume, okay, times the volume itself, of course, okay. So now if we combine, let me highlight the equations that we're combining. We're combining this equation, right, into here, right, then we'll get sigma NB times V. Sorry, I didn't put it all together next to each other, right? Times NA times V, right? So that's the second thing that we're putting in, okay? Okay. All right, so this gave us sort of a complicated, but hopefully some interesting concept of what we're trying to calculate here with this rate, okay? So there's this cross-section thing, which is where all the underlying physics, you know, are important things are, right? And we're gonna separate this out in a second, okay? And it's the number density of particle B, number density of particle A, times some volume, times the speed which they are crossing each other, okay? So the rate is kind of like the number of target particles, right? And this part is the flux, this part is the cross-section, right? I really love that he switched all the orders when he write these equations, okay? So what we can do is solve this equation for sigma, right? We just divide both sides by all this complicated NB, NA, and then the two V's, right? One capital, one lowercase, right? So we can think about the cross-section as just kind of number of interaction, right? Which is what this rate is, okay? Per unit time, actually, right? Because the interaction with the rate is how many interaction per second, okay? Right? Divided by the number of target particles, which is this piece here, right? And then the incident flux, okay? So what we're gonna do in our calculation is that, well, except the convention is that, right? We're gonna make the calculation so that we're gonna normalize things so that we have one particle per unit volume, okay? That means V is equal to 1, NB is equal to 1, NA is equal to 1. So that makes a lot of the math easy, okay? Before we jump to the next equation, and this rate up here, right, is exactly what gamma Fi is, right? This transition rate, okay? So we have that on top. Just gonna highlight the same stuff on both, okay? And then what happened is that, right, this V down here, right, is the relative speed between the two particles, okay? And then we made everything else equal to 1, okay? Okay. So is this definition of the cross-section okay with everyone? Right, we just have there's a rate, right? And then the rate is going to be proportional to the cross-section, which is going to be times the flux of particles that's passing each other, right? And most of that flux actually cancel out if we just use this convention of making the volume equals to 1, the number density equals to 1 on both. And then it's actually just the relative velocity between the two particle that matters. Okay. So basically, the cross-section is the transition rate divided by the velocity between the two particle crossing each other, okay? In this normalization of one particle per volume, per unit volume, okay? In real life, if you work at the LHCs, they're going to be colliding 10 to the 15 particles together, so you have to multiply by that. But that's easy to deal with in the when you know the what's known as the luminosity of the beam. But for now, we're just trying to get to the physics, which is calculating this cross. What is this cross section? How do we get to that, right? Okay, so that's what we have. Okay, so now we're going to try to plug in what we learned from the Fermi's golden rule. So remember from the previous section, right? The Fermi golden rules is this complicated long equation, right? That has, so this is for the 1 to 2 decay, right? Where we have energy of the mother particle decay into 2 daughter particles, and then the momentum also and these delta function basically enforces conservation of energy and momentum, okay? But then we have to integrate this, these triple integrals over momentum, okay? Does there anyone why there's a bunch of 2 E's on the bottoms here? Remember that? Maybe on Zoom. Why are there a bunch of 2 E's on the bottom? Guys, a second to find the unmute button.
Does it have anything to do with normalizing for invariant matrix?
Right. So remember, initially, this was not MFI, right? This was TFI, right? The transition matrix, right? And basically the TFI is the MFI divided by square root of 2e, right? And that's why we have a bunch of 2e's on the bottom, okay? Okay. Of course, there's going to be a bunch of 2pi's around, but that's not the, that's just from converting from linear to spherical coordinate systems. Okay. All right, so in this case, right, instead of a particle decaying from A to 1 and 2, right, now we have 4 things to keep track of, right? We have particle A coming in, particle B coming in, they smash into each other, right? And then a new particle 1, particle 2 comes out of it, right? Not necessarily with the same, it could have a different mass, it could have a different momentum, right? Between the incoming and outgoing, but right, the sum of this momentum has to equal to the sum of the outgoing, right? PA plus PB equals to P1 plus P2, right? And this is you can use this as the four vector notation, right? So that means the energy is conserved, and then the 3 momentum is also conserved, okay? So in the collision case, right, now we have 4 things instead of 3, right? So what we need to do is actually add an EB, right? Because that's the conservation of EA plus EB is going to be equal to E1 plus E2, okay? Similarly, with the momentum, right, you have to add the 3 momentum of the outgoing incoming B particles also, right? Okay. Okay. Right. Fortunately, right, this stuff on the bottom here doesn't change because this is only the outgoing guys, right? Okay. This part does change because now we have 2 incoming particles, right? So that gives you a factor of 2 times the energy of A times 2 times the energy of B. That gives you 4 EAB, right? So that's what this whole factor in front does, okay? By converting from, right, the transition rate to oops, let me go to the left here. To cross section, what you do is you divide by VA plus VB, right? So that's where this VA plus VB came from, okay? Right? Otherwise, everything is the same. We're just changing a few things, right? Okay. This thing in the denominator is actually going to be very important. It's known as the Lorentz invariant flux factor. Okay. The reason it's called flux factor is because, right, V8 plus VB is proportional to the flux, right? Right. The bigger the relative speed is with each other, the more the 2 particles will cross each other, right? And therefore give you a bigger flux. Okay. And the reason it's Lorentz invariant is because, well, you actually going to multiply it by EA and EB, which you can prove after a bit of kinematics and a ton of algebra. Okay, which is gonna, I think the first one, either the first or the second homework problem, right? You can prove that it turns out to be this 4 vector multiplication, PA dotted into PB. Okay, so in Thomson, unfortunately, I think he does not always follow his own convention, right? So this dot product, right? When he does this dot product, he really means, you know, PA mu PB mu. But I guess one of them has to be downstairs. Okay. You're literally doing the 4 vector dot product. Okay. This is a 4 vector dot product.
Yeah, I think I was wondering about that myself, Wing, and I think the fact that they aren't bolded is the way he's trying to signal that they're 4 vectors instead of 3 vectors.
Yeah, but sometimes he writes 3 vectors without bolding them either.
Oh, okay.
Yeah.
Oh man.
Yeah. So that's why in the homework, so in the homework, what I asked you guys to do is actually, like, if there's a 3 vector, you want the magnitude of that, right? You just put a star next to it, right? That's the convention that he defined in the first chapter, but then he's not following it in chapter 3. Okay. But that's okay. We figured it out. Okay. Right. But dot products between things that are not bolded so far has definitely been for 4 vectors. Okay. And you can figure out, you know, in context, does he mean 4 vectors or does he mean 3 vectors also, right? Okay. So, but it does take a little bit of thinking before you can figure out which one is which. Okay. So this is going to be an important factor because, right, it turns out to be a Lorentz invariant. Okay. Because when that factor is Lorentz invariant, we can do this calculation in any frame of reference we want, right? And our favorite frame of reference is the center of mass frame. Okay. The center of mass frame is really nice, right? Right. In fact, why this is shorter, right? That means, right, whatever momentum, 3 momentum of particle A, 3 momentum of particle B coming in, they are going to be equal and opposite each other, right? Right. That's a nice frame of reference. Okay. In fact, what the Thomson decided to do is just call this PI star. Okay. Okay. This is the, and now, right, once again, he's doing a different notation. When he calls stars in this case, all the stars means values in the center of momentum frame. Okay. So this is still a 3 vector, but in the center of momentum frame. Okay. Right. And of course, you know, PI, right, 3 vector has to be equal to PI 3 vector out. Okay. The incoming and outgoing momentum has to be the same in order for you to conserve momentum, right? So these two are equal to each other. And in that case, what happens is that momentum 1 and 2 also are going to be equal and opposite each other. Okay. So in fact, this is probably not a nice drawing of that. So particle 2 pi comes out like this, right? Or the back to each other. Okay. Okay. And using one of the Mandelstam variables, Mandelstam variable. Okay. I know this is a special variable, square root of S. It stands for the center of mass energy. Square root of S. Okay. It's the center of mass energy. Okay. It's basically going to be the sum of the energy of particle 1A coming in, particle B coming in their reference frame. Okay. So this is only valid in the reference in the center mass frame, because remember, energy is not Lorentz invariant, depends on which frame of reference you're using, right? Okay. This gives you some simplification of the Lorentz invariant factor. Okay. In this particular frame, I'm going to let you go through the algebra and fill in the steps that Thomson made. Right. You're going to find that it's just going to be 4 times the incoming momentum. This is the 3 momentum. Okay. The magnitude of the 3 momentum. Okay. Times the square root of S. Okay. Which is the sum of the 2 energies. Okay. Okay. So if I was writing this book, this will be bold, right? Okay. It's the center of mass energy, which is just EA plus EB in the center of mass. Right. Actually, Ivan, can you repeat saying something? I wonder if the people on Zoom can pick you up, actually.
Is the square root of S the center of mass?
It's the center of mass. Can people on Zoom hear Ivan? He spoke with this mic.
Yeah, we
I
can.
can hear him.
Okay, nice. Okay, so everybody can talk. Perfect. All right, nice. Well worth investing $60 on this. Okay, so we can replace this, you know, Lorentz invariant factor in our cross-section calculation with this, right? The 4 times the 3 momentum magnitude, okay, times the square root S in the denominator, okay? In fact, right, since up here, if I go back up, to our original calculation, EA plus EB, right? That's also this in the center of mass, that will be this the center of mass energy also. Okay, so I can replace that. Okay, and then since PI equals to P final in 3-vector form, we can also replace most of those PAs and so PA plus PB, right? We can replace them with just P1 plus P2. Okay. And now we just have to evaluate this integral. Okay. Evaluating this integral is the same, it's very similar to the process we did for the decay calculation, where we basically, well, we knock out one of the PD D3P2 by enforcing this delta function, okay? And then we replace all these E2s in terms of, square root of a bunch of momentums and masses, right? And then we can actually enforce this delta function, okay? And all of this, okay, with a few steps that I'm not gonna try to go through in class, right? It's gonna give you a factor of PF, which is the final outgoing momentum magnitude, the 3 momentum magnitude of either of the particle, right? The reason you don't have to keep track of both of them is because their magnitude is going to be the same. They're just going to be equal in opposite direction, right? Okay, remember P1 star is going to be equal to P2 star, right? So you can even put the little bars around it if you want. P2 star, right? It's going to be whatever PF stars. Okay. Put the little ball. And there's a few factors of 1/4 and that came out because of this delta function evaluation, but we'll skip that. Okay, so this allows you to calculate the the cross section. I don't know why I took differential cross section of a particular process of 1 to, you have some incoming particle 1, incoming particle B, right? They exchange something between them, and they're going to the outgoing particle 1, outgoing particle 2. Sorry, I think I probably said 1 and 2 initially. So the incoming particles are always A and B. The outgoing particles are 1 and 2. Okay. So this is more of a Feynman diagram picture, right? T is this way, and then basically the distance between them is the vertical. We still don't know what's happening in here, right? The stuff that's happening here is all in this MFI. Okay. And we're gonna spend 2.5 chapters to get to that for one of the simplest interactions. Okay. Which is just electrons scattering off each other. Okay. All right. Okay, with that, I don't think I assigned any homework on this particular thing because this MFI gets really complicated, and we just want to just have it for you guys when we are able to calculate this MFI in 2.5 weeks, then we can actually put that in, okay, and then we'll actually evaluate these momentas. Okay.
Once we can do the MFI components, are we going to go over all of the equations that have that in there again? Because it'll
yeah, basically we're going to be calculating this, but we're going to figure out how to calculate this MFI thing. Right now we just have this kind of starter equation, right? I think Griffiths does have a simple example of this in his book on the scattering. I'm trying to remember. But those are going to be like toy example that doesn't exist in real life. So, but similar to what we did with the decay process, right? What we did last Friday, on Friday, right? You could plug in some simple. Sorry, I think I copied and pasted things. You could put in some simple numbers in there and just calculate some numbers and get some values out of it, just like you would with this equation, where you assume MFI has no angular dependence, right? Remember this integral is actually just over the angle of the outgoing momentums. Okay. So once we have the angular dependence on how these particles couple to each other, then we can actually compute this integral. And then we can actually have just a number as an answer, right? As opposed to just an equation. Okay. So speaking of the angular dependence, there's more to this, right? Okay. Right. Since there's this angular integral here, what we can do is we can define something called differential cross-section by taking the derivative of both sides of this, right? It's just, should have saved myself more space, right? And by taking the derivative with respect to the solid angle here, right, you basically knock out this integral, okay? What you can do is you can define this thing called a differential cross-section, which is just d sigma, okay? Okay. Well, usually d omega will be down here, but Thompson decided to write it on the right-hand side, but that's okay, right? It's basically the same thing here, but just without that integral sign, right? Okay. Okay. This is actually one of the most interesting things that a lot of places actually measure, because, right, remember all of the, you know, the actual physics, how these things couple to each other is inside this matrix element factor, right? So if you can measure how the angle that the outgoing particle comes out of, you can actually constrain what is going on with this MFI, right? Because what happened is that if you measure just the total cross section, right, up here, right, you wash out all the angular dependence, right, which is useful, right? So if you're trying to smash proton and protons together, right, you don't actually care what, you know, which process happened. You just want to smash them together and make other stuff, right? The total cross section is important because you want to figure out, you know, how fast you want to smash two particles together, right? And how many of them, right? And that way you can get a rate equation out of it. Okay. But, right, if you want to figure out the details of actually how they're scattering off each other, right, that's going to be inside this MFI, which has an angular dependence, right? Okay. So this cross-section, so this differential cross-section, this cross-section depends on has an angular dependence, right? And because of the matrix elements, okay? This matrix element is going to depend on angle because the spins of the particles that are involved, okay? So the reason why we can't even do the simplest cross-section for electrons scattering off each other is because, right, remember from chapter 1 when we drew these Feynman diagrams, right? Okay, an electron, right? Now we have an incoming particle. We're going to call that A, right? Whatever, momentum A, momentum B, right? And this outgoing momentum 1, momentum 2. Okay. What happened is that, right? If these were spinless particles, right, then we can actually calculate what this MFI is, which is going to be actually proportional to whatever these coupling constants square. Okay, but right, the electron has 1.5 spin. Okay, and this gamma has a spin of 1. Okay, and what's going to happen is that they're going to have some angular dependence on how this vertex are calculated, and we're going to find out how we can actually do that in chapter 5, actually. Okay, when we learn this thing called the Feynman rules for interactions. Okay, so this electron is having spin, photon having spin. That's going to complicate things. That gives you these angular dependence. The other thing that also gives you angular dependence is actually the coupling between different types of vectors and scalars. And I don't want to go into that right now, but that's going to cause some interaction to only go in a particular has a high dependence on which direction things actually will interact with each other. Okay, and that's going to be basically the next 4 or 5 chapters of our life. So in order to solve this, right? So right now we haven't really even talked about this thing called the Dirac equation. Okay. So one thing is that the Schrodinger equation, remember this, the Schrodinger equation, there's probably some i's involved, right? Negative i's. whatever that wave function is, times the Hamiltonian, right? Times that wave function. And this Hamiltonian's usually, you know, something with second order derivatives of psi plus some potential function times that psi acting on that side, right? So one of the problem is that you have a first time derivative here, and then a second spatial derivatives here. Okay, this is inherently not Lorentz invariant, right? Right, the rate of change in as a first derivative in time, but then that's equal to the rate of change in space in the second derivative, right? This is where we're gonna see that the Schrodinger equation is not going to be able to allow us to make the full, give us the full picture of actually what's going on in relativistic quantum mechanics. We're not going to dive into relativistic quantum mechanics, but we are going to derive, well, to tell you how the Dirac equation came up through this thing called the Klein-Gordon equation, where instead of these things being wave functions, they turn into these things called spinors, which are has 4 components. Okay, and this is going to be allow us to actually make a spin, a plus spin electron, right? Oops. Let's just write them out correctly. S equals 1/2 electron, and then the next one will be a spin minus electron. Okay. What do you think the other 2 things are? If we're dealing with the same particle. And positrons, yeah. And this is actually going to be forced upon us with the mathematics of the Dirac equation, which is going to be the foundation for the quantum electrodynamics, which is going to be in the next couple of chapters, okay? And so the Dirac equation actually predicts the existence of antiparticles in 1928, okay? And then luckily for Dirac, 4 years later, they actually found it, okay? And like Peter Higgs, where he had to wait like 45 years. Okay. And this is actually the first evidence for antimatter, where this is a picture of a cloud chamber. I don't want to talk about detector too much. But what happened is that they probably did a magnetic field. Let's see. So if it's positive, B cross A. Yeah, so that magnetic field is probably coming out of the board. Okay. Let's remember this silly notation. Okay. If you have a positive charge coming through here, it's going to curve to the left on this board. If you have a negative charge, it's going to curve to the right. Okay. And what they found was that the stuff that curves to the right, most of the stuff curves to the right, and these are the electrons. But then sometimes we would get stuff that curves to the left instead, and these are the positrons. And they would have similar mass, you know, up to the ability for them to measure at a time, because their radius of curvatures are the same as each other. Okay. Right. And this is going to allow us to, you know, Dirac literally just predicted antimatter, and there it was. Okay. Okay. So that's all I want to cover for the differential cross-section and the cross-section stuff. We're going to come back to this in more detail once we can figure out how to calculate this MFI thing. But for now, how do I go back to having a